My name is Malachi Dyer, and this is my presentation on biomechanics A2, on which I'll give a detailed analysis on movement within sport. I'll firstly analyze distance and displacement, then lead my way through to speed and velocity. Distance can be defined as a space between two given areas. It is a scalar quantity, meaning that it has a sense of magnitude and not direction. It is usually measured in meters for short distance events and is found through the product of speed and time. Distance is crucial within sport analysis as it can be used to monitor things like intensity and capabilities of an athlete. It can also be used to find displacement, speed, and velocity, which I will cover in later slides. Distance can be tracked through technology such as GPS and some apps such as Strava for running. A sporting example of this could be through a marathon, through using the equation, the average speed of the athletes multiplied by the time it has taken to complete the marathon will give the distance covered. If the average speed of the athlete was 3.5 meters per second, their time was 12,060 seconds or 3 hours and 21 minutes, the product of these would give a distance of 42,000 meters or 42 kilometers, which is the length of the marathon. Displacement is a vector quantity, meaning that it has both a sense of direction and magnitude. It can be defined as a change in an object or person's position relative to a reference frame. This means that if an athlete was to run around a 400-meter track and go back to their starting position, the displacement of the athlete was zero, as they have not gone anywhere. This is different to distance, as distance of that exercise would have been 400 meters, and it does not have a sense of direction due to it being a scalar quantity. Displacement can help find how far something has traveled in which direction. This can be done in sport by using a tracker on an athlete. In football, this could be through a GPS or a monitor, which can find positioning at certain points within a match or training session as they can sense direction and distance away from their starting point. A sporting example of this principle could be used in a 50-meter swimming race, where the athlete will travel 50 meters in a 50-meter lane, leading to the overall displacement to be 50 meters. Speed is a scalar quantity. It represents a change in distance over time, which can be used to measured in meters per second. Speed is very important within biomechanics in sport, as the analysis of it can be compared to all sorts of previous data that can help the athlete to develop in their sport depending on what their sport requires. Speed can be found through dividing distance by time, possibly using a distance time graph that I'll explain in my next slide. A sporting example of this can be calculated through a 30-meter sprint test. This is a test designed for measuring an athlete's speed and acceleration to be used compared to all sorts of data such as normative data. Knowing that speed is equal to distance divided by time, we know that the distance travelled will be 30 meters, and this athlete has performed this in 4 seconds. Dividing 30 by 4 will give the speed of 7.5 meters per second. Bringing these together, a distance time graph gives a visual representation of the distance over time. These are very useful when representing data in an easy and simple way rather than having lots of loose numbers. A lot of athletes are very visual learners as well, which makes this a lot more helpful in terms of a visual aspect. It is also useful for coaches and analytics teams within a professional level to see visually an athlete's performance. Looking at this presentation of distance time graph, the y-axis represents distance and the x-axis represents time. The splits are the areas between the two letters. Analysing these, split A to B is showing a constant speed. To find the speed on this graph, we need to find the gradient. This is found by dividing the change in x by the change in y. As we see here, from point A to point B, 2,500 meters have been travelled. I'll change in y, and this has taken 16,200 seconds. This gives the speed of 0.19 meters per second. Moving on, from point B to C, the object is stationary as the gradient is 0. From point C to D, there is a bigger increase in speed as the gradient is steeper than the first. Then from point D to point E, the object is stationary again. There is then a constant speed travelling back to the starting point. Velocity is another vector quantity. It is essentially speed with direction. However, velocity has two ways to be used within biomechanics. First, which comes under distance time, where distance divided by time equals velocity. The second way it can be used is when trying to find momentum or mass. A sporting example of when velocity can be calculated. The first way could be through a frisbee. If the frisbee is thrown 30 meters west and it takes 7 seconds to get there, the velocity is 4.3 meters per second west. Using the second way, an example of an arrow with the mass of 0.1 kilograms whilst having the momentum of 7 kilograms meters per second would result in the velocity being 70 meters per second, as velocity equals momentum divided by mass. Bringing it all together, velocity time graphs are extremely useful when trying to visually represent acceleration, velocity, and time during an athlete's performance. Acceleration is the rate of change of velocity of an object with respect for time. An example of how it could be used in sport could be through a car driving, such as an F1 car or an Indy racing. In split A to B, car is accelerating slowly as the gradient is steeper than 180 degrees. From point B to C, the car is accelerating quickly as it is at a steeper gradient. From point C to D, the car is at a steady pace as the velocity is staying the same. Now from point D to E, the car is rapidly decelerating. From point E to F, it is accelerating in the opposite direction. And from point F to G, it is at a steady speed in the opposite direction. Thank you for listening.